Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 10th module in a series that we're recording to support the course EE221A, which is linear system theory at Berkeley. And the topic of today's module is that of orthogonality and adjoints. Last module, we defined the inner product. And now that we've got this concept of an inner product space and this function of that we've defined in terms of its properties, an inner product, we can start to think about some derivatives of this definition of inner product and perhaps give a geometric interpretation in some cases to what this means. And so let's start by looking at the concept of orthogonality, or of a space, a subspace of a vector space being orthogonal to another space, another subspace. Okay, so let's, we'll start by looking at orthogonality. And as before, we'll start with our Hilbert space. We'll call it H over the field F endowed with an inner product. So this is our Hilbert space. And we define orthogonal. We define it, first of all, between vectors in the space H as follows. So two vectors, x and y, both in H, are orthogonal if their inner product is equal to 0. So if and only if, by definition, the inner product between x and y is equal to 0. Okay, so we talked last module about some examples. In particular, we talked about in Rn or Cn that the inner product, the standard inner product, is simply the dot product between those vectors. So in, for example, in R2, if this were a vector x, y is orthogonal to x if its inner product is 0. So it's a vector that's going to be perpendicular to the vector x. Okay, so in R2, there's kind of a very nice simple geometric interpretation for orthogonality of vectors. But as we know, we're generalizing to vector spaces which are not necessarily Rn or Cn, for example, function spaces. And so we generally define orthogonality as being the inner product between those vectors being equal to 0. With that definition of orthogonality between vectors, we can now talk about subspaces that are orthogonal to each other. So if we had a subspace M, so this is a subspace, M is a subspace of our vector space H. So M is a subspace of H. We define M, and we'll use this term perp, coming from perpendicular. So M perp is defined to be those vectors y in H such that x inner producted with y is equal to 0 for all x in M. So M perp is defined to be all of those vectors still in the parent vector space which are orthogonal to every vector in M. And M perp is called the orthogonal complement of M. Of M, the orthogonal complement. So orthogonality of vectors, orthogonality of subspaces, and we can say some interesting things here. We can show, for example, just from this definition, that the only intersection between M and its orthogonal complement is the 0 vector. So if you wanted to show that M intersect its orthogonal complement, M perp, is equal to the only thing in that intersection is the 0 vector. So that's how we write it. It's the set whose only element is 0. We could show that as follows. So I would probably show that in the same kind of style that we would show uniqueness, for example. Suppose that we had a vector x in that intersection which is not equal to 0. So suppose I have a vector x, and let's make x not equal to 0 in M intersect M perp. Okay, so by definition, that means that x inner producted with y is equal to 0 for all y in M. But since it's in the intersection, it also means that since x is in M, but since x is in the intersection, it also has to be in M. So that tells us that x inner producted with itself is equal to 0. But if that's true, we know from our definition of inner products that that must imply that the vector x is equal to 0. But this means that x is equal to the 0 vector. Okay, so we tried to start with a non-zero vector, and we showed very quickly that the only way that these properties could hold if it's in both the if it's in the intersection, so if it's both in M and M perp, is that x is equal to 0. So we derive the contradiction here. Okay, so we've defined orthogonality of vectors. We've defined orthogonal complements of subspaces. We've showed that a subspace intersected, the only vector that is common to a subspace and its orthogonal complement is the 0 vector. So now let's move on to a very important concept, which again is building on this concept of an inner product, and that is called adjoint, the adjoint map. Adjoints. Okay, an adjoint is defined in terms of an inner product. We're going to think about spaces, again, where our field is either the reals or the complex numbers. We'll endow the space with an inner product, so we can think about a Hilbert space. So again, let's go back to our map here, our map notation. Let's consider a space U and a space V. These are both inner product spaces, so we have an inner product on U, and we have an inner product on V. And let's think about a map, A, from U to V. Suppose A is continuous and linear. So we're going to restrict ourselves to continuous linear maps A. Then the adjoint of A which we'll call A star, is defined as follows. It's defined very simply in terms of the corresponding inner products on U and V. So A star maps V back to U. Okay, so A star is defined as the map from V back to U, such that V, if we think of a vector V and V, inner producted with AU, and that's using the inner product over in the space V, is equal to A star V U, and that's the inner product over in U. Okay, so the adjoint map A star is a map from the codomain of A back to the domain of A, and it maps as, it's defined as follows, simply in terms of the inner product, that this inner product between elements in V, so we've got a vector V and we've got a vector AU, so that inner product is happening over here, is equal to A star V, so that's an element back in U, inner producted with U. And that's a complete way to define what we call an adjoint map. All right, so what does that mean? How do we now translate that to thinking about adjoints of popular, interesting maps that we use all the time? So here's an example. This is a nice example because it draws out the different kinds of inner products we could use over different spaces. So here's an example. Let's just keep our diagram on the board. We're going to define the space U over here to be the space of continuous functions, continuous vector-valued functions. So here U is equal to the space continuous functions defined from the interval t0 to t1 of the real line over to Rn. So that's our space U. And our space V will just be R. Okay, so then when we talk about the inner product in that function space, we're using the standard definition of the inner product in that function space. So, and when we talk about the inner product in V, it's just going to be the dot product between two elements in V, which in this case, we're just going to be multiplying them together. And we have to now define what this map A is. So A is taking functions to real numbers. A maps C, the space of continuous functions from t0 to t1 to Rn to R. And it's defined as follows. A takes a function f, which belongs in that function space, and maps it to a real number, which is the inner product of that function f with a function g. Okay, and here g is a given function which belongs in the same space. So that inner product is the inner product over in U. So the map itself, this example is a little tricky because the map itself is defined in terms of an inner product. And we would like to compute A star, the adjoint of that map. So A star is going to take real numbers back to functions. Okay, so the question is find A star. What is A star? All right, so let's do this. We define A star in terms of the inner product on the appropriate space. So if we look at a vector V and we take the inner product of that with A applied to a function f. Okay, so this is our operator notation. A is taking a function f and it's giving us a real number, and we're going to take the inner product between that real number and just some other real number V in our vector space V. So that's our inner product space in V. Okay, that's just the standard inner product in R. So it's equal to V star, and it's going to be V star multiplied by the real number, which is A operating on F. So A operating on F gives us this real number over here. So that's just G inner producted with F. And that's the inner product taken in that function space, U. Okay, so that's equal to V star. That inner product is the standard inner product, as we said, on that function space. So that's the integral from t0 to t1 of G star of t. These are vectors in Rn now. F of t dt. So we learned that that's the standard inner product on a function space. And that's the pointwise inner product integrated over the time period t0 to t1. All right, and now we're almost there. Now we have to try to rearrange it to get it into a form which is going to look like A star V, comma F, and then pull out what A star is. So here we can rewrite that now. Now this is just algebra here. I'm going to bring V inside the integral sign, t0 to t1 of V. Okay, so that t0 belongs to the bottom of that integral, of V g star of t, f of t, dt. Again, that's just the standard pointwise inner product. Okay, but that's nice because that's just equal to V g f, inner product with f. Okay, so now I can look at this and I can say, okay, but that's in a form that we want, because that's, if I compare this inner product here, and I write that as A star V inner producted with F, it tells me that the operation of A star is to take an element V and to multiply it by this function G. So basically from this analysis, we come up with a definition for A star, or we extract what A star is. It just takes vectors V, so elements of the reals, and it gives us a function which is just VG, where G is the thing that we used in the definition of the map A. It's the function that we used in the definition of the map A. So here, the operation of A star is to simply take a real number and multiply it by the function G. Okay, so what have we done in this module? We've defined, based on our definition of inner products, we've defined what it means to be for vectors to be orthogonal. We've used that to define what it means for subspaces to be orthogonal to each other, or if you have a subspace, how do you define its orthogonal complement? We looked at properties of orthogonal complements. And then the last thing we did, a very important thing, is to define the adjoint map. Given a continuous linear map, so we restricted ourselves to maps A, which are continuous and linear, not necessarily between finite dimensional vector spaces, but they're continuous and linear, then from that we can derive an adjoint map, which also, by the way, turns out to be continuous and linear, defined through the definition of the definition of the inner product. And so from that definition, we had a nice example which illustrated how you would derive the adjoint map given a map and given the properties of the inner products on the underlying spaces. Thank you very much.